So let me introduce Naomi, and she's going to take it away from here.
Thank you so much. This is amazing. When we first talked, me and Ashley, I was in the UK. It was middle of pandemic, I think, and we spoke on the phone. And I was in like a 2 meter by 2 meter room, doing my PhD, like writing my thesis. I was in a very dark place. And yeah, everything's much better now. Now I live in Maryland, which is very fun. Very different to Leicester in the UK, where I'm from. So I thought I would start with a little bit about me. So my accent obviously is not from the US. I am from near London, about an hour outside of London, in a place called Newbury, if you know England. And I did my 4-year integrated masters at Leicester, University of Leicester, with physics with astrophysics. And I did that and graduated in 2012. And then I ended up back in Leicester for my PhD that I finished in September just last year. And my thesis was looking at the atmospheres of the ice giants, Uranus and Neptune, using the SPITZER Space Telescope infrared spectrometer, and I'll come to why that's important later. And it's the reason why I'm involved with the JWST now, and the ice giants are some of the most interesting targets of the JWST in the future, and obviously in the past now, which is exciting. And I moved out to Maryland just in October last year, and now I work at NASA Goddard Space Flight Center. So this is what I'm going to be talking about today. I'm going to start by explaining what the JWST is, so right at the beginning. Then I'm going to outline its general use for solar system science. Then I'll talk a little bit about something called the guaranteed time observations, which you'll come to understand what that means in a moment. And then I'll go into a little bit more detail on the ice giants, because they're my favorite. So I'll start with, what is the JWST? Why is it so special? So the James Webb Space Telescope is an orbiting infrared observatory. It has a 6.5 meter primary mirror made of 18 separate movable segments. It has 4 scientific instruments, all housed in the back of the mirror. It has a tennis court sized 5-layer sun shield. And all of that was stuffed into a rocket, launched into space, and slowly unfolded itself as it approached its home 1.5 million kilometers away. So it's a pretty special telescope. It's also the premier observatory of the next decade. It's going to serve thousands of astronomers worldwide. And this past year has especially been amazing. I've never really seen scientists be this giddy about science before. They've really been excited about everything that's happened. And building it has been an international collaboration between the European Space Agency, NASA, and also the Canadian Space Agency. So how does the JWST work? It works like any other telescope, really. The main job of any telescope is to look at distant objects and to gather light from those objects, and it focuses it either into your eye, like a telescope you'd have at home, or into instruments or multiple instruments if it's bigger. And the JWST is unique because it's the first ever space telescope with a movable mirror segments. All of them are individually movable. And it needs to be movable because we needed to fold that telescope into the Ariane 5 for launch. And also, we need to adjust each individual telescope mirror so that we can focus it remotely, because we're not with it like we are with telescopes that are on Earth. Also, when we adjust it remotely, it's very important that we can do that, because when Hubble went up, we needed to actually send astronauts to be able to focus it because it was slightly unfocused. So we need to be able to do that when it's 1.5 million kilometers away. So this is really an amazing piece of technology that hasn't been used in space before. And we'll get to the 4 individual instruments later. So the easiest way to explain what the JWST is to compare it to the Hubble Space Telescope, everybody's favorite telescope until JWST. And it was launched back in 1990. Fun fact, it's the exact same age as me, pretty much, almost. And it celebrated 30 years, obviously, back in 2020. And it's had over 1.5 million observations since its launch, and it's produced beautiful images of all sorts of things, especially ones of the solar system that I'm most interested in. It's observed things from Mars all the way out to Neptune, just like JWST can. And some of its biggest discoveries include that it found 5 new moons of Pluto, and it's also been observing multiple impacts at Jupiter. So imagine what the JWST can do with even better technology. So how is the JWST better than Hubble? By the way, everybody says it's the scientific successor to Hubble, but they are going to be working together simultaneously. Hubble is not dead. It's still going strong. We can come to who the successor of, so the JWST is a successor of a telescope and not Hubble. So for telescopes, bigger always means better. So this is an animation showing the relative size of the Hubble Space Telescope on the right and the JWST on the left. And you can see that it's a much larger mirror. That 2.4 meter mirror looks tiny, even though that person down there looks really small. And you can see the really immense scale of both of these observatories. And the fact that we managed to launch them and put them in space is amazing. But with a larger mirror, you can look at dimmer, smaller, colder, more distant objects than something with a smaller mirror. Another major difference between the JWST and Hubble is the different wavelengths that it senses in. So Hubble is mostly in the visible, whereas JWST focuses on the infrared. And so visible light, what we see with our eyes, is what Hubble mostly sees. And so when we split light up into a prism, into a rainbow, towards the violet end of the visible spectrum, we get ultraviolet, and Hubble can also sense in the ultraviolet. And when we go to the red end, we also can go beyond that into the infrared, and instead of seeing light, we feel it as heat instead. And that is what the JWST can look at the heat. And JWST sees in the near-infrared, which Hubble also can, and also further into the mid-infrared. And you see the video here, it shows how useful seeing in the infrared is. So you can see a nebula, lots of dust and gas in space. And first, I'll let it play again. You can see it in the visible first. And that means that you see all of that dust and gas, and it's very beautiful, but it's very annoying for scientists to not be able to see through the dust and gas and actually see what's going on. So, absolutely beautiful photo taken by Hubble, but if we see this next picture, which is taken in the infrared by SPITZER, then you can see through it, and you can see those stars being born, and you can see other processes happening, which are very interesting to scientists. And you can also use this for the solar system, so this image here behind me is Jupiter in both visible and infrared, and it helps us to see through the gases and hazes of the atmosphere to be able to sense deeper circulations and chemicals, and it's all very useful for scientists. So because we're looking at heat instead of light, it needs to be kept much colder than Hubble. Earth is very warm, so we need to go much further away. Hubble is at around 570 kilometers from Earth in a close Earth orbit, whereas we have to go all the way to the L2 Lagrange point with JWST, and that is 1.5 million kilometers away, or around 1 million miles. And a Lagrangian point sounds confusing, but it's just a gravity well. So it's where a spacecraft can be placed and kind of hover/orbit around this gravity well, and it can stay in constant communication with Earth as we travel around the sun together. So there are 4 instruments aboard the JWST, all housed inside the ISIM, or the Integrated Science Instrument Module. There is the near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the mid-infrared instrument, or MIRI, and the fine guidance sensor, or the FGS NIRIS, which is kind of like two instruments, but it's all in one instrument package. So these instruments provide imaging and spectroscopic capabilities across the whole range of wavelengths. And so when we think of Webb, we kind of think of the astrophysics and the cosmology that were first released when we saw what was happening with JWST, this first science, these distant galaxies and Big Bang, etc. And Webb has four major science themes, not just those themes that we saw. So we have first light and reionization is looking back over 13.5 billion years to see the first stars and galaxies forming in the early universe. Then the second one, assembly of galaxies. You see Stefan's quintet, and galaxies, that helps us to understand how these galaxies assemble over billions of years. And then number three, these birth of stars and protoplanetary systems. Helps us see through that dust and gas in those nebulas to see where those planetary systems are being born. And then the last one is the one that we want to talk about today. And when we think about planetary systems and the origin of life, a lot of people go straight to exoplanets. But we have our own planets to look at. And there's no better way to understand how planetary systems in general work than by looking at our own planetary system. So it's a very large and important area for JWST. So looking at our own solar system with JWST. And not many people knew that this was going to be used to look at our own solar system. Most of those big releases were about the beginning of the universe, etc., nebulas, galaxies. This image here is still the background of my desktop computer, so it's gorgeous. It was until this was released. Everybody was like, wait, we're looking at Jupiter with JWST? And everybody was like, yeah, we are going to be looking at a lot of things with JWST in our own solar system. And these were the first JWST images of an extended object in our solar system. We were already looking at asteroids, etc., but this was the one that made people go, wow. And these are the images that we got from just commissioning. Commissioning is like we're kind of testing the telescope, making sure it doesn't break when we do certain things. When we look at something bright, to make sure that the instruments all work. When we look at something moving, we can actually track that moving object, and everything in the solar system is moving. So this is Jupiter, some of its moons, and even its ring you can see, which is amazing just for a test. So what in the solar system is JWST actually going to be looking at, going to be able to look at? We can observe everything from Mars out. So we have to make sure that the telescope stays cold. So the mirror and all the instruments behind that mirror have to stay as cold as possible. So that means that our massive silver umbrella has to stay facing the sun. So we can never turn towards the sun and look at things like Venus or Mercury. But we can look at, or Earth. So we have to look at everything Mars out. So we can look at Mars, all of the giant planets, we can look at asteroids, we can look at comets, we can look at Kuiper objects. And that's quite difficult for a telescope that was primarily designed for looking at things in the distance. Because things like galaxies and things that are really far away, they're very dim because they're much dimmer than things like Jupiter, for example, very bright. And also they're very stationary on the night sky. So engineers had to overcome these obstacles to be able to track things very quickly, and also to be able to look at things bright things without breaking any of the instruments. But luckily they did get over all those problems. So for planets and rings, we're going to be looking at Mars all the way through to Neptune, and there are restrictions on the amount of brightness that we can put in the telescope still. So we have to use the right instruments and instrument modes for different planets to make sure that we don't overwhelm them. And for the planets, we can look at their atmospheres and also their rings. We can look at clouds, we can look at hazes, we can look at circulation patterns, we can look at composition. So we can see what they're made of, we can see what the weather is like and why it's like that. And we'll come back to these a little bit in more detail to see what's happening in this next year, and also the ice giants, which are my favorite, so we'll spend a bit more time on them. So it's not just planets that we're looking at, but also their moons as well. And the moons of the solar system are some of the most interesting targets in the solar system. For example, Europa and Enceladus, also known as our ocean worlds or our icy moons. And they're cold, but they might harbor life underneath these crusts of ice. They may have these subsurface oceans that could contain life. And then there's also Titan, which is one of my favorite moons because it's the only body in the solar system that has oceans, rivers, and streams, just like we have on Earth, except instead of it being made of water, like our oceans, it's made of methane, which is a bit of a crazy thought, but it could contain life, but it would be life unlike what we know. So it's difficult to kind of know what to look for. And this is an image actually from the Cassini infrared instrument. And so you can see how the infrared allows us to penetrate the haze, very thick haze that's at Titan, and be able to look at the surface and the lakes happening underneath. Then there's also asteroids and comets that we're looking at, or primitive bodies. And these are of huge scientific interest. And all the people in my department always focus on small bodies, and I'm sick of hearing about them, but they are quite cool. They're very small and faint, so JWST is one of the only telescopes that can really look at them properly. And they're the leftovers from the formation of the solar system. So asteroids like Didymos and Dimorphos, you may have heard in the news recently about DART, or the Double Asteroid Redirect Test. And that happened, and at the same time as it happened, we were looking at it with as many telescopes as possible. I think every telescope on Earth was pointed, and off Earth was pointed towards this one asteroid, or two asteroids. And this is a DART time-lapse of the impact happening. So the DART spacecraft smashed into the smaller of the two moons, asteroids, and this is the kind of plume and explosion that happened afterwards, which is amazing that we're able to look at it with JWST so soon after JWST has been said okay for science. And this is an even more amazing achievement when you realize that these two asteroids were traveling faster than what they decided was the maximum speed limit of JWST. It was actually double the speed limit. And with the help of all of the team at Space Telescope, they managed to test and make sure that we could actually use it at the speeds that this was going at so that we could get these images. So really amazing that we can go double the speed limit. And these objects contain answers to some of the biggest questions. So they can help solve mysteries of the early solar system and planet formation, and maybe even some of these brought life to Earth. We just don't know. And also other forms of primitive bodies are Kuiper belt objects, or KBOs, or sometimes called trans-Neptunian objects, or TNOs. And asteroids are mostly in that asteroid belt between Mars and Jupiter, but KBOs are beyond Neptune in the Kuiper belt. And so that means that they're colder and further away, which means they're even harder to detect than asteroids. And JWST is going to be able to characterize every known KBO to date, which is amazing. And they've already started doing all of that. It's very, you always see, I don't know if anybody follows the Twitter that says what JWST is observing, but it's a very fun Twitter. And it's always saying names of Kuiper belt objects. I'm like, can we get round to some planets, please? And you might think you don't know any KBOs, but Pluto is one. And also, the largest moon of Neptune, Triton, which I do care about, that is also thought to be a captured Kuiper belt object. So my job at the moment is to support solar system scientists who will be using the JWST in something called the GTO program. And guaranteed time observations are programs that are awarded, so time on the telescope that is awarded to a scientist that has contributed significantly to either the hardware or software components, or maybe helped plan the observatory's scientific mission. And one of my bosses, Heidi Hamill, she was a scientist that was awarded time, and she decided to gift it to the solar system community. And so she's now one of my supervisors, along with Stephanie Milam, who's the JWST Deputy Project Scientist for Planetary Science. So myself and my colleague Ian, who's my small bodies person, he does all the boring stuff, and I do all the cool stuff. And we work on this, I work on everything planetary, and yeah, Ian's everything small bodies. So each of these bullet points is a program that has a team of scientists from many different institutions all across the world who are looking at their targets in the first year of JWST operations. So we work with those scientists in getting them from data through to publishing their science. We're also both on the moving target and scattered light commissioning teams, and that means that we're helping still to get the JWST ready for optimum science. And I'm going to talk about my 7 programs and give you a little insight into what's already been done and what is still planned. So I'm going to start with our closest neighbor, Mars. And it's one of the fastest objects that JWST can track, apart from the DART thing. It's also one of the brightest, because it's so close to us, and it's also quite warm compared to other things we're looking at. And we managed to make global maps of Mars, like this one shown, which doesn't look like a lot, but it really is when you think about how big Mars is and how hot it is, and that we didn't break anything when taking this image. And it's really given a lot of hope to anybody else looking at anything, because they know that they won't saturate the detectors, because we've done Mars, and if you could do Mars, you can do anything. And we also looked at it using the NIRSpec instrument, which gets us spectra instead of images. So this was taken with NIRCam, so images and NIRSpec. So that splits up the light, so it treats the disk of Mars as kind of a point source, and it will just take a slit of that light and spread it out and show us what is made of. And it managed to detect water, so that blue part there, and that's never really been done before in these wavelengths, so that's really exciting. And this is going to help us to answer the big questions, like what happened to those ancient lakes, oceans, and rivers on Mars? Why did they dry up? Could Mars ever have hosted life? And was it in the distant or the recent past? And what was the weather like? And that kind of question is very important if we're planning to ever send humans there. Then there's Jupiter. Jupiter is the largest and also one of the most challenging objects to observe with JWST. It's big, so you have to mosaic multiple images together to get something beautiful like this. It doesn't just come out of the telescope like it, although it is close. And we've used MIRI to determine the 3-dimensional temperature structure and composition of the Great Red Spot for our GTO program. And this happened back in July time, where they took these images, and it helps us to really understand what's going on at different depths in the Great Red Spot. You notice we're only looking at the Great Red Spot with the GTO program, whereas we're seeing a lot of other things happening with Jupiter, and that's not the GTO program, it's actually something called the ERS program, or the Early Release Science program. And that is a team of, a very big team, I think it's about 50 people, and they're using every single instrument mode to look at Jupiter and its entire system, so moons, rings, atmosphere, anything they can get their hands on. And they're doing that to test all of those modes to make sure that we can actually do the science we want to do in the solar system, which is really exciting. So Saturn hasn't happened yet. These are all Cassini images, or these two at least are Cassini images. And we're targeting the whole Saturn system. So we were only doing the Great Red Spot before for Jupiter, but now we're targeting the whole system because there's no ERS program for Saturn. And following the conclusion of Cassini in 2017, we're hoping to get some results that will kind of fill in the gaps between Cassini and the next orbiter that goes to Saturn, because we really want to know what's happening at Saturn all the time, because there's still a lot of unknowns about Saturn and about its atmosphere, about its rings. Why did it have such amazing rings? We just don't know. And loads of things about the magnetosphere. Like there's lots of things that we still don't understand, and also about this its pole. So when we're going to be what we're going to be focusing on is the pole and the rings with the MIRI instrument specifically, to be able to look deep into the pole and see what's going on and why is it hexagon shaped. We just don't know. And we're going to be targeting 2 of the most interesting moons in our solar system with 3 instruments again. And this is going to be starting very soon. We're going to take high-resolution observations of the jets emanating from these moons. So trying to measure the contents of what's underneath those deep, icy crusts. This will reveal information about the processes acting beneath the moon's ice crust and the potential for the habitability underneath them. Specifically, do they have these hydrothermal vents like we have on Earth? And if they do they or can they host life? And then we're going to be looking at Titan, again, also very soon. And we want to advance our understanding of Titan's gases, hazes, clouds, and surface composition. And again, this is a near-infrared mosaic from Cassini. And it shows the sun reflecting off of Titan's north polar seas, which is just beautiful. And really, it is one of my favorite moons, if not my favorite. I think it might be my favorite. So now on to my actual favorites, the ice giants. So the GTOs, the only GTOs right now that are missing are Uranus and Neptune. And I hope you all saw this. Yep. Yeah. This image is like my favorite. It was the one that I was most excited about. It's the first ice giant observation from JWST, and we haven't had any since. Unfortunately, they've all gone behind the sun, annoyingly. So this was our first opportunity to look at Neptune. And when I first saw this image, I didn't realize I was even looking at Neptune, because we've never seen the rings look like this before. Even Voyager didn't capture as much detail as this. So I was the subject matter expert, and as the subject matter expert for this, I helped with the raw data, so taking the raw data from the telescope, which doesn't look as good as this, and making it look better than this. Sorry, not better than this, but better than the raw, and then sending that to the artists, so Joe De Pasquale and Alyssa. We sent it to them, and they did their magic and created this. And it really is amazing. I mean, the background galaxies really gives you a sense of scale of the universe and how small even something as huge as Neptune is. So why is this so exciting? Mostly because we don't know anything about Uranus and Neptune. So this animation here, you can see each line shows a path of a spacecraft mission, and Uranus and Neptune are extremely lonely out there. We've even been to Pluto. It's ridiculous. So we've only used one spacecraft to actually look at these planets in situ, and that is Voyager 2. Voyager 2 flew past Uranus in 1986, and then flew past Neptune in 1989, just a couple of weeks each as it flew into interstellar space. And that's it. That's where we get those 2 images that you think of when you think of Uranus and Neptune. That's just from the Voyager 2, and that was before I was born, both of those things. So we really, really need to go back. But this is why there's so much remote sensing happening, like with JWST. So remote sensing just means looking from a distance. So any telescopes that we use on Earth, that's all remote sensing, and any telescopes we use in space, that's also remote sensing. And so we really have to rely on that. And that's what I do. So what is an ice giant? And what makes an ice giant an ice giant? Mostly it's the size. They're smaller than Jupiter and Saturn, but bigger than Earth and the rocky planets, and also the stuff that they're made of. So they're made of the same things as Jupiter and Saturn, so they have hydrogen and helium as their main base chemicals, but they have a higher concentration of these things are called ices. And it's not ices, it's ices, because in this kind of chemistry, when you say ices, it's actually anything that has a is heavier than hydrogen and helium, so it's basically everything. And so things like methane, which give the ice giants their blue color, and the same methane that gives our sky the blue color when you look up, is the same thing giving them their blue color. And there's also a lot of water inside them, we think. So this illustration here shows what we think is going on inside these ice giants. And it gets very strange. At the surface, you have the atmosphere and hazes that I study. And then as you get deeper, things get weirder. So as you go down, you get hotter and more compressed and more pressure. And so that means you get something called supercritical water ocean, which is very hot and dense water. And then below that, it gets even stranger still. You get something called superionic ice, which is extremely hot and black and very dense, and it's where all of your oxygen atoms are kind of stacked together like a solid, but then all of your hydrogen atoms can kind of go between them, so it conducts electricity very well. And then below that, we think we have a small rocky core. But again, all of this is just speculation. We haven't been to it enough to understand what's going on inside. This is just the best guess of scientists. And there is so little that we know about them. There is a guy that I work with who has been trying to fight for the fact that they should be called rock giants rather than ice giants, because we just don't know enough to be able to call them ice giants. So that's how little we know about them. And so I've already talked about the similarities and what makes them ice giants, but there's also a lot of differences. So Uranus is kind of the weirdo of the solar system, and Neptune is normal. So guess which one's my favorite? It's Uranus. And so it has an extreme axial tilt, and that just means it's rotating on its side. And it's unlike anything else in the solar system. No other planets or bodies are rotating on their sides like this. And Neptune has an Earth-like axial tilt, so kind of 20 degrees, what we have that gives us our seasons. And again, another weird thing about Uranus is that it has very little internal heat. We can't detect any heat going on inside. Like every other planet in the solar system has internal heat, and that kind of powers the circulation and the weather systems, the atmosphere. And so we end up with a sluggish atmosphere at Uranus and a normal / very active atmosphere at Neptune. So it's some of the highest winds in the solar system at Neptune. And Uranus has a lot of small satellites, which is probably the most normal thing about it. And Neptune has this large captured satellite, Triton. So Neptune is the one that we looked at first, and it's very distant. To give you some scale, 30 AU means that it's 30 times the distance of the Earth to the Sun. So 30 times the distance away. And it's extremely far, and 164 years to get around the Sun doesn't sound too much when saying it, but in the time that we've had telescopes that are powerful enough to look at Neptune, we haven't been able to see its North Pole. We haven't seen its North Pole yet. We've only ever seen its South Pole. So that puts it into context of how far this thing is away and how long it takes to go around the Sun. And as I said, when I saw this image, I didn't realize that it was Neptune because we'd never seen its rings like this. I mean, everybody was saying, oh my gosh, I didn't realize that Neptune had rings, I didn't realize that Jupiter had rings. Neither did I, and I'm a planetary scientist. I just don't work in rings, so it's fine. And these are some of the best ring images that we've seen since Voyager 2, and Voyager 2 even missed some things that we are now seeing in these images. And the moons, there are 7 out of 14 of the moons. I mean, my boss insists that she can see the 8th one that is here and that it's there. It could be. Every time I look at it, it looks a bit more like it's there. Maybe it's just wishful thinking. So maybe 8 moons out of 14, and the other ones are off the screen, so we can't see them because they're not in the field of view. So we are seeing all of the moons that we can see. And the atmosphere, which is what I work in, the features that we're seeing are at wavelengths that we've never been able to look at before, because we've not had the ability to really look at Neptune in this wavelength range at this kind of spatial resolution. And here's some of the details that you may have missed in these. So I just really wanted to point out the faintest features. Not only can we see the rings, we can also see these faint ring arcs. So this part here is not a trick of the eye. It is looking slightly brighter than the rest of the rings, and that is, these ring arcs are kind of like a failed moon. They're just a lot of dust and rocks that have accumulated, and they rotate around the planet with the rings, just like a moon does. And so they create these arcs, and they look like they're here in the back. And if you look at the models, then it should be there. So it's really exciting that you can actually see it from JWST. And there's also, we can see the ring, the Gal ring, which we really didn't think that we would be able to see, because it's so faint and diffuse, but we can see it. And then to give you some context as well, this point of light here is Naiad, which is a moon that is only 60 kilometers in diameter. And when we're looking 30 times the distance from the Earth to the Sun, being able to see something that's 60 kilometers in diameter is pretty astonishing. And if we look closer at the atmosphere, this is in 2 different wavelengths, so that the beautiful image that the artist created is using 4 of these wavelengths, and this is 2 of them. And you can see the bright features are clouds, methane clouds that the sun is reflecting off of. And then when it's a bit darker, that means that we're looking deeper into the atmosphere and we're seeing methane emission. So it doesn't look like blue unless we're looking invisible, but in infrared it looks like darkness. So all of these first images that we've really been looking at, apart from Mars and a couple for Jupiter, have been with NIRCam. And so those images with Neptune were all NIRCam images. And in the future, we want to be able to look at them with these 2 specific instruments, NIRSpec and MIRI. So why these 2 instruments? So we've been looking at this NIRCam imaging mode, whereas we want to look at these 2. And it's specifically because they have this integrated field unit. And an integrated field unit sounds complicated, but it's just the ability, so when you take a picture, every single pixel in that picture has a spectra that you can look at, like a really detailed spreading of light to be able to see what it's made of and what temperature it is. And every single pixel in the picture will be able to tell you something. And to be able to understand why that's really amazing, we have to go back in time to 2003 when SPITZER was launched. So SPITZER Space Telescope is what I used for my PhD, and it's a massive advancement to get the JWST because this was such a small telescope. Like, it was great, but it was also a bit rubbish compared to Hubble and compared to JWST especially. But it was very exciting because you could see into the mid-infrared and also into the far infrared, but I was only using the mid-infrared instrument on SPITZER. And it has a 0.85 meter mirror, and that mid-infrared or infrared spectrometer is between 5 and 37 microns, which is similar to the MIRI instrument on JWST. So why is the mid-infrared important, especially for the ice giants? These are some example images of Uranus from visible through to the microwave with other space-based and ground-based telescopes. And we can also apply this to Neptune. They're very similar in that respect. And these different wavelengths are sensitive to different depths in the atmosphere. So on the right here, that shows the vertical structure of an ice giant atmosphere. So pressure on the y-axis. And this shows the stratosphere and the troposphere separated by the tropopause. So everything below the tropopause is the troposphere, and everything above it is the stratosphere. And we can see where each of the wavelength bands senses. The visible and the near-infrared in purple and blue, like for the Hubble Space Telescope, it looks at the cloud tops, so around the 1 bar level. And whereas microwave looks deeper into the troposphere, but the mid-infrared can see a lot more. It can see into the troposphere, the upper troposphere, and also into the stratosphere, which is very unique in wavelength bands. And this is really exciting for ice giant scientists because we want to look at these photochemical hazes because it's very important chemistry that we can see with them. And this is the kind of data that we get from SPITZER. It's very boring, I know. I had to spend my whole PhD doing this. And this was the most exciting stuff that we got because this is Uranus compared directly to Neptune spectra. And that's really exciting because we've never really been able to directly compare them before in this manner. So you can see we're splitting up the light, remember, and each of the bumps and troughs is telling us about a different species. And it's also telling us about the temperature of the planet. And so you can see Neptune has a warmer atmosphere, remember, even though it's further away from the sun, because Uranus doesn't have that internal heat that we're looking for. So you can see that lack of internal heat, where you can see more noise, and you can also see that it's lower down and has a lower temperature. Whereas at Neptune we can see much more defined bumps and troughs that show us that it's higher temperature, we have less noise, which is very useful. And this is the kind of global average of the results from SPITZER, because with SPITZER we don't get any images, and that's why it looks so boring, because we can't see a picture with it. And that's because it's so small. And a lot of these spectra that we see, this is like an average of everything that we get. So it's an average of all of the longitudes, so as it spins around we get lots of different images, lots of different point sources, and also as we go in time we can also see a lot of the same stuff. So these different times that we're seeing show different sides of the planet. So as it's rotating, so this is Uranus in 2007, so remember Uranus spins on its side like that. And my PhD investigation split up the different longitudes to see if anything was changing between them. And so the plot on the left here shows the different longitudes of the observations that come from Uranus in 2007. And so the question was, do we see a difference between one side of the planet and the other side of the planet? And the answer was strangely yes. We weren't expecting that answer. And you can see on the right, the first time we saw these changes, so the longitude 3, which is in green, is lower radiance than we see with L4, which is in purple. And to be able to see this a little bit clearer, we did some different analysis. So we look at each chemical species in the spectrum, shown by the bands in different places. And each species contributes to a different height in the atmosphere. And this plot here shows the contribution for each pressure. So everything above the tropopause, remember, is the stratosphere, and everything below the tropopause is the troposphere. So as an example, methane here it contributes to the stratosphere, whereas two different chemicals, you've got CH3D, which is like a different type of methane, and hydrogen and helium, they contribute to deeper in the troposphere. And so what we did was we plotted the variation of each species for the whole 360 degrees as it rotates. And you can see that in the troposphere, for those tropospheric species, nothing's changing over the whole 360 degrees, whereas with methane, which is in the stratosphere, it's changing a lot. And we found this exact thing with all of the other species as well. And so we had to try and figure out what's happening and why this would be, because it's the opposite of what we thought. We couldn't find these same variations at Neptune. And Neptune is the historically more active atmosphere, so if anything was going to vary, it was going to be Neptune, not Uranus. So when we saw this, we had to answer why. And that's very difficult with a telescope that doesn't give you any images. So we had to think what kind of physical process could be causing it. So we looked at some images from Keck, and we found some storms that could be the answer, but again, we're not sure. Is it caused by temperature? Is it caused by composition changes? So we did some modeling, found out it might be temperature, but we don't know. So everything's just a guess until we can get JWST. So in comparison to SPITZER, JWST is a massive step up. So the 6.5 meter mirror is a massive step up from the 0.85 meter mirror of SPITZER. My favorite kind of scale, being able to compare the two, is that SPITZER is the same size mirror as this secondary mirror on the JWST, which is huge, because that secondary mirror is just used to bounce the light back into the instruments, which really puts into perspective how much bigger JWST is. And the instruments are also more advanced on JWST, and they're more sensitive. They have better spectral coverage, they have better spatial resolution, and they have better spectral resolution than SPITZER. And SPITZER's died now, so it's definitely the successor to SPITZER, we can say that now. So what about Earth or ground-based telescopes? Because they're a lot bigger than the JWST. They're huge, they're 10 plus meters in diameter. So the three of these images are from the VLT, or the Very Large Telescope, that's in Chile. And one of them is from the Keck Telescope in Hawaii. And it shows how detailed we can see from the ground. But because we have something called telluric absorption or atmospheric absorption, it gets in the way of what we want to see. So there's a lot of water in our atmosphere, and the one thing that a lot of scientists want to find out there is water. And if our water is blocking us being able to see other water, then we definitely need things like JWST that's away from our water to be able to see that. And we can get these good images, but unfortunately, we can only get it in those few spectral windows that we have. So we've seen that we currently frequently have to choose between information or image. So the information that we get from SPITZER Space Telescope, we don't get an image with it. But with ground-based, we get those beautiful images, but we don't get any spectrum, we don't get any information with it. And that's why the JWST is so groundbreaking, because we can finally get information and image together. And we can use these IFUs, and my favorite part about the IFUs is, remember, each pixel is has a spectrum, and so they've named it, this isn't me making it up, this is real. Spectra plus pixels, spaxels. It's my favorite word in the whole of science, it's great. And that's extremely exciting for all scientists involved, for even looking at deep images of galaxies and nebula, being able to see information and image at the same time is just super exciting. So both ice giants have this guaranteed time observation, or GTO time, on the JWST. And there's a fair amount of allocated time, so enough to map 360 degrees, 3 longitudes of Uranus are being observed, and at the end of the year, hopefully. and 2 longitudes of Neptune are being observed in summer of next year. And both will be observed in both the mid-infrared and the near-infrared. And these are the main science goals of the GTO. And we still know very little about them, so they're very broad science goals. We want global maps, so to be able to know what they're made of. We want to look at why they're different, so we want to directly compare the two. We want to look at their atmospheres. We want to look at climate, seasons, weather. And yeah, directly comparing them is a massive thing in ice giant science. Why is Uranus so weird? We don't know. And one thing I wanted to mention at the end, I recently got awarded Hubble time, which will look at both of the ice giants at the same time as the JWST. So not a successor, they're working together for better science. And this is an example of how Hubble and JWST can kind of make each other's science better by working together. So what Hubble can do that JWST can't, it can look in the visible wavelengths, and it can also look in more detail than the IFUs or those spaxels. So with spaxels, so this right image here is a model of what these spaxels will look like for Miri when looking at Uranus. And you see we kind of compromise a little bit on what the planet looks like, but remember each of those pixels is going to have a spectrum associated that's even better than SPITZER. So it's worth it. But it would be great to also get these Hubble images at the same time to be able to get the amazing detail in the atmosphere to understand a little bit more. And also in the visible is the only wavelength range that we can see dark spots. Just like the great dark spot at Neptune during the Voyager flybys, we want to be able to see dark spots because they could mean something amazing we still don't understand very well. They could be like the great red spot, but why do they keep disappearing, coming again? We don't know. So last section, I'll just tell you some things to be excited about. So first, JWST observations of Uranus haven't happened yet, so that's hopefully coming soon. The NIRSPEC and MIRI observations of both of the ice giants haven't happened yet. That will be coming soon. And Saturn, icy moons, and Titan should be in the next month to 2 months, so look out for any press releases for that. And JWST Cycle 2 is about to start. So the Cycle 1 is still happening, but scientists have to think ahead and start thinking about what they want to do with the telescope next. So they're going to be writing lots of things to try and convince people that they can use the telescope for it for the next year. So that's coming up. And also in the Decadal Survey, which is kind of the document that tells NASA what to spend their money on, that has prioritized a flagship mission to Uranus in the next 10 years. So hopefully we'll be able to get to Uranus in the 2040s at some point, and we'll be able to do an orbiter and probe, which is very exciting. There's going to be a lot of Uranus probe jokes out there. And I'll leave you with a couple of links that are very useful. NASA's amazing with their information. And if you want to follow me on Twitter, then you can find out more about JWST and also the ice giants. Thank you.